Unfortunately, batteries are running out. But how can we understand that? It was Walter Nernst who showed that with his famous equation, the Nernst equation. We are going to show how that works with several examples. Osmotic behavior of salt and fresh water, the famous Daniell cell based on zinc and copper, and in the end a concentration cell of nickel sulfate. Concentration differences of salt in water can be used to create electricity, as we will show, and what battery in the end concentration creating of energy is known as osmosis, a process that is going on in your own body every second, keeping you alive. But how does it work? Imagine you have a beaker with a high salt concentration and you pour very neatly water with a low salt concentration. Then after a while the concentration will be leveled. This is what you see here with a yellow iron sulfate solution, and not a solution of rock salt because that is colorless but would behave basically the same. It means there has been a transport of salt, and that is kinetic energy. This kinetic energy we would like to use for converting it into electricity, and that is what we show you here. Blue energy is perhaps one of the most unexploited sources of green energy. Blue energy can be seen as osmotic behavior when fresh water of a river meets salt water of the sea in the estuary. A chemical process similar as occurs in our living body allows for electricity generation once an adequate system is being developed to harness it. How does that work? Concentration difference of salt in water can be used to create electricity, which is referred to as blue energy. It works as follows. We place two vessels against each other, separated by a membrane that does not allow salt to pass. The only species that are allowed to go through it is water. That means to arrive at a concentration that is the same at both sides, water molecules go from the left vessel to the right vessel, leading to a difference in height. This height is potential energy and can be regarded as pumped hydropower that can be converted into electricity by releasing that water and driving an alternator. This whole idea can be used to place huge installations at the place where fresh water meets salt water, not surprisingly where a river flows into the sea. Despite the size of such a system, the actual energy density remains low, but the size itself is massive and will certainly compensate for the overall storage capacity. The other interesting thing is that the battery will not run out as long the river supplies fresh water. However, in a confined system where there is not a constant replenishment of fresh water, the voltage starts to fade and drops finally to zero when the concentrations are the same. This will happen in all batteries, and to give you an idea how the voltage evolves in such a situation, we will show you this via the well-known Daniell cell. The Daniell cell consists of a negative electrode of metallic zinc in a solution of zinc sulfate and a positive electrode of metallic copper in a solution of copper sulfate. These electrodes are connecting each other via a salt bridge where ions are free to migrate to compensate for the electric charge that evolves because of electron transport that occurs via the external circuit, where the electron will do their work. Once they are doing their job, meaning a load is applied, in both compartments a reaction takes place. At the negative electrode, metallic zinc goes into solution as zinc 2 plus ions, giving up their electrons to copper ions in the other compartment, where these ions precipitate as metallic copper. Charge compensation is maintained by ions that flow through the salt bridge. Positive ions will govern the electrons, whereas negative ions go the opposite direction. During work, the potential will drop to lower voltages. Let's take similar sizes of compartments at the negative and positive electrode and concentrations of 1 molar of zinc and copper sulfate and a fresh cell. Now let the battery work, and during work we measure the concentration of the copper ions, and at the same time we measure the voltage. We will obtain a curve that you can see here on the left hand side. If we now plot the data where we take the logarithmic of the copper ion concentration, the curve becomes a straight line. This indicates that the measured voltage should be linearly dependent on the concentration. This is indeed what has been found by Walter Nernst, and he figured out that the measured potential in each compartment depends on the concentration according to the well-known Nernst equation that says the measured potential of the zinc compartment is equal to the standard redox potential as defined as 1 molar minus a certain term of R times T over N times F times the natural logarithmic of 1 over the zinc concentration. Here R is the gas constant, 8.314 joule per mole Kelvin, T the absolute temperature in Kelvin, and the number of electrons involved in the reaction, and F the Faraday constant, which is 96,485 coulomb per mole. A similar relation was found at the copper electrode. Together this gives the overall equation relating to the zinc 2+ and copper 2+ concentrations. If now the zinc 2+ concentration increases at the same time the copper 2+ decreases, the logarithmic factor increases and thus the potential drops. It turns out for this cell that for every increase in the concentration by a factor of 10, the voltage changes by roughly 30 millivolts. This then can be also explain the measured voltage of an osmotic cell. If we now take a nickel cell with various nickel sulfate concentrations, one compartment with a concentration of 0.001 molar and the other one with a 1 molar concentration, the cell voltage is roughly 3 times 30 millivolts, giving 0.09 volt. This cell can do the job till the concentrations in both compartments becomes the same, which is roughly 0.5 molar in each compartment. This is also what we could measure for the seawater and the freshwater system, taking a concentration difference of 1000 times.